Welcome back to the C programming language in action. In this module, we're going to learn all about input and output as provided by the C standard library. We've already been using C's input and output facilities in the form of the Printf function, but here in this module, we're going to take a closer look at Printf, but also at the other core functions that are used to read and write to the console and read and write to a file on disk. This is sometimes called C's IOStream library, but don't confuse this with C++'s IOStream library, an altogether different beast. Whereas the C++ IOStream library is strange and incredibly slow, C's standard input-output library, while also offering a stream abstraction, is blazingly fast. It's one of those areas where C completely outshines C++. Let's take a look. The mighty Printf function is an amazingly powerful and fast text output engine. It provides facilities for formatting all the fundamental types with various options, bells, and whistles. The major challenge is that it's not nearly as universal as it could be. While there is a Printf function accompanying practically every C compiler, of the handful of compilers I use regularly, all of them support a slightly different dialect. When I use Visual C++, I normally write something like this to print out an integer. D and I seem to be largely interchangeable, but assuming all compilers support D for integers, they don't automatically support larger integer values, perhaps 64-bit integers. Consider this. That's too big to fit into a 32-bit integer. Let's see what the Visual C++ compiler does with that. The compiler is satisfied, but the result is wrong. How about GCC? Once you get through all the painful options, the GCC compiler, like a few others I've tried, immediately picks up a problem at compile time, which is a nice touch. It recognizes that the argument type does not match that expected by the format specifier. So what should we use instead? Well, this is where it gets tricky, and you end up having to go with trial and error until you find what works reliably on each compiler and platform. GCC is particularly troublesome as it doesn't directly specify what format Printf supports, but adopts certain characteristics from whatever environment you used to build the GCC compiler and where it's running. Here, I'm just going to give you some examples from Visual C++, as it's one of the most widely used compilers and has a stable, supported format. It should give you a good sense for what is available. You may just need to use the preprocessor to conditionally change the formatting if and when you need to support other compilers that may require a different format specification. The Visual C++ compiler supports 64-bit numbers, specifically with the I64 formatting argument. Let's try that. That's much better. Similarly, you can use the I64 argument to print out 64-bit numbers in hexadecimal notation as well. If you're dealing with regular integers, you can of course still print out hexadecimal numbers. You just don't need to include the I64 argument. If you don't like those lowercase alphanumeric characters, no problem. Just use the capital X format specifier. And of course, if you like the OX preamble, to make it obvious that we're looking at a hex number representation, you can of course include that as well. But that has nothing to do with formatting. Of course, Printf is full of dark secrets. You can also print the leading OX without spelling it out. But now the X is in capital, which is a bit weird. You can opt for a lowercase. But now everything is in lowercase, not just the X. Anyway, there are some things you can do with integers. There are many more, but that should get you started. Let's now look at floating point numbers. Well, that's where you're typically concerned about things like the number of digits following the decimal point. First, the default. So the default is to format the number with 6 digits following the decimal point. The most common thing to do is to limit this to some reasonable value according to your presentation needs, perhaps 2 digits. Notice how the result is rounded. 0.456 was rounded to 0.46 to fit into 2 digits. How about alignment? That's where the width specification comes in. This tells you the minimum number of characters to be written to the output. That way we can align output to some virtual cell boundary. Here's what it looks like for this floating point number if we wanted to print out the result so that the output consumes at least 10 characters. So if you look carefully, you should be able to count 10 monospaced characters, including some white space that was added to the front of the line. And let's add an integer just for contrast. This too is padded to ensure 10 character output at a minimum. So we can see that they're automatically right aligned. But what if we need them left aligned so that the extra white space is added at the end to ensure any subsequent output is aligned properly? No problem, just negate the width specification. Like that. Let me just add some pre and post text so we can see this left alignment in action. So even though it doesn't look like it lines up here, if all goes well, the output should line up in 3 distinct columns. Sure enough, the numbers are left aligned, and the next virtual column is also properly aligned thanks to the padding introduced by the width specification. What about strings? Well, that's easy enough. Here's a message. The S specifier, not surprisingly, will print out a null-terminated string. Cool. But what if you only want a substring printed? Perhaps the string is not null-terminated. No problem, just prefix the length. Note I didn't say hardcode the length in the format string. That would be incredibly limited, although it's possible. Often you have some substring that is only known at runtime. How would you print out that substring? Like this. Let's say we need to print the first 11 characters. We can use the special variable length specifier. Let's see. And there you go, the first 11 characters providing hello world. Nice. Alright, that's enough printf tricks for now. Next, we need to consider strings and security. What is about printf is that it's not just designed for console output, and you can in fact use it to write formatted output to a file or even a string. Let's say we need to format some simple HTML. We have a desired font or font family. And a desired font size, and a message to present with our choice of font and size. Now we need to prepare a buffer to transmit over HTTP, so we'll begin with a large enough buffer. Assuming a sufficiently large stack, we might use a local stack variable. On an embedded device, you might want to use the heap instead. Here a simple character array will suffice. And then we can call the sprintf function, like printf but with an S prefix, denoting that this variant will format the result into a character string buffer. Font, the size, and the message. Now, I may not win any awards for HTML style or etiquette, but this is nevertheless adequate HTML for any browser to display. sprintf's first argument is the buffer to which the formatted output will be copied. Then there's the usual format string, followed by a set of values to be inserted. And then let's just print the buffer to the console so we can perform a visual check that the formatting is correct. Notice that while I could have passed the buffer directly to printf, that's in general quite a dangerous idea. The problem is that if there's anything in the buffer that might be interpreted as formatting specifiers, then the printf function may be confused, expect additional arguments, and once again, an attacker may use this to exploit your app. Here we avoid the problem by simply using a straightforward formatting string to print out the buffer's contents. Okay, let's take a look. The Visual C++ compiler doesn't like the sprintf function. How about GCC? No problem there. Let's just check the output quickly. Okay, so that looks fine. I won't bother to show it to you in the browser. I'm sure you can imagine the text "Hello World" in a large, clear font. But what's the problem here with Visual C++? Well, it comes down to this. The sprintf function has no idea how large this buffer is. Let's go back to the code. Here, the sprintf function really has no idea how large this buffer is. It is going on faith that you have provided a large enough buffer to accommodate the formatted output. But what if the combined HTML and message exceeds 500 characters, including the null terminator? This is nothing specific to the Visual C++ compiler. It affects the GCC compiler just as much. That compiler simply doesn't pick up on this threat. But let's see what happens. We can easily simulate this simply by using a smaller buffer. After all, sprintf doesn't seemingly care how big it is. Let's see what happens with GCC. Again, it compiles fine, but running it causes a problem. Let's try that again. The program has crashed, but notice that it crashed after the message was printed out, seemingly at the end of the program. Let's try it with the Visual C++ compiler. Again we have the warning, but notice that we're getting a compiler warning, not a compiler error message. That means that although it's warning about something, we can still expect an executable, and let's give it a try. And sure enough, much the same result. The message is printed out, and it looks perfectly fine. But then the program crashes. Let's have a look at that code again. What's happening is that the formatted message is nearly 100 characters long, but the buffer only holds 50 characters. How's that possible? Well, the buffer was allocated on the stack. The stack itself is much larger than 100 characters, so the sprintf function appears to work fine. it just happily carries on writing past the end of the buffer. The printf function then takes that same buffer and prints it out. Again, it doesn't care that the buffer's size was exceeded. So far, so good. But when that main function returns, things fall apart, since the stack has been destroyed, and that means the main function cannot reliably return. In fact, modern compilers place guards around stack frames to catch stuff like this in an attempt to avoid further exploits. Visual C++ does anyway, but we should not rely on that. We need to write our code more securely. Well, what can be done? Well, that's where we can take a closer look at that Visual C++ compiler warning. The warning says sprintf, this function or variable may be unsafe. Consider using sprintf_s instead. So the C standard library that ships with the Visual C++ compiler has long offered some secure alternatives for many of the notoriously unsafe standard library functions, such as sprintf. Functions that write to buffers absolutely must check those buffers are in fact large enough. Fortunately, a safer alternative to sprintf is provided. Let's correct this. The _s suffix denotes a secure alternative to the sprintf function, but notice that it now expects an additional parameter to specify the size of the provided buffer. Let's give it a try. This time, no complaints from the compiler. But it still crashes. That's right, the buffer is too small, and the secure sprintf function terminates the app. But notice what didn't happen. Even though it still crashed, it crashed far sooner than before. It crashed inside the secure sprintf function intentionally. The previous version formatted the message, printed it out, and only crashed much later when the stack was unwound. All that time, an attacker can find opportunities to exploit the application. Now, the application is torn down immediately when an unrecoverable problem is encountered. Incidentally, if we were using C++, this becomes even simpler, since the standard library can make use of function templates to make this even simpler and less error-prone. We can simply remove this argument with the size of the array. If you compile this with a C compiler, it will certainly fail, but a C++ compiler will find a matching function template that will deduce the size of the buffer at compile time. Okay, enough about formatting strings.